All right, so now that we know how to compute eigenvalues, we can now leverage this to compute eigenvectors. So just as a reminder, an eigenvector is a vector of A that satisfies the equation AX equals lambda x. And the problem with finding eigenvectors is that we don't know what this lambda is. So once you find the lambda, then we can solve this equation. And what we're going to do is we're going to just move that lambda x on the other side and solve this equation, ax minus lambda x. And we can factor out that x, and this becomes a minus lambda I times x equals to 0. So if you know the eigenvalues, then the eigenvectors are just solutions to a minus lambda I x equals the 0 vector. All right, so this is fairly straightforward. So typically the first step you're going to do to compute eigenvectors is you have to compute the eigenvalues. So let's just jump right into an example. So we have this matrix right here, 9, 1, 1, 9. And what we're going to do first is we're going to compute the eigenvalues. And we're going to do this by finding the characteristic polynomial. So the characteristic polynomial, we're going to subtract the lambdas on the diagonal and find the determinant. And that's going to be 9 minus lambda squared minus 1. Or 81 minus 18 lambda plus lambda squared minus 1. And that's 80 minus 18 lambda plus lambda squared. And this factors as 10 minus lambda and 8 minus lambda. So lambda is going to be equal to 8 and 10. All right, so that's a simple example of computing the eigenvalues. And now to compute the eigenvectors, we're going to compute the eigenvectors by solving a minus lambda I x equals the 0 vector for each lambda. So we have to do this once for each lambda. And so keep in mind, the reason we're doing this is because we want to find a vector where ax equals lambda x, and that's the same thing as a solution to a minus lambda ix equals 0. So any solution to these equations is going to give us an eigenvector. So we're going to have lambda equals 8 first. So 9 minus 8, 1. 1, 9 minus 8. So we're going to solve this equation right here. And the 8, we're going to subtract the 8 on the diagonal. All right, so we're just going to put this in row reduced form, the augmented matrix. And now we're going to row reduce. So we're literally going to use everything in the book to find these eigenvectors. So we can take row 2 minus row 1. And that's going to give us, and then this tells us that x plus y equals 0. So we have, or in other words, y is equal to minus x, or rather x is equal to minus y. So we have a free variable right here. So that tells us that y is going to equal y, and we have xy is equal to minus 1, 1. All right, so this right here times y. So this tells us that there's an eigenvalue, of 8 has eigenvector minus 1, 1. But more precisely, it tells us that any multiple is also an any multiple is also an eigenvector. All right, so this brings us to the first fun fact that's important. So because the eigenvector, since eigenvectors solve ax minus lambda x equals 0, or in other words, a minus lambda I x equals 0, is the same as the kernel of a minus lambda I. So we know the kernel is a subspace. So the eigenvectors solve this. So the eigenvectors, all eigenvectors of A with a specific eigenvalue form a vector space. So it's going to be, in this case, the set of all eigenvectors with eigenvalue 8 form a line generated in the minus 1, 1 direction. So it's fair to say minus 1, 1 is the eigenvector with eigenvalue 8. But just keep in mind when we say the eigenvector, we really mean any scalar multiple of that vector. We treat those as kind of equivalent in the context of finding all the eigenvectors. Right, and now we're going to repeat this for lambda equals 10. So lambda equals 10. We now have 9 minus 10, 1, 1, 9 minus 10. And we want to solve when that is equal to 0. So we're going to put that into an augmented matrix. And we're going to perform roughly the same row operations as before. Now we add the rows. And I guess if you want to put this in strict reduced echelon form, we're going to go ahead and make that minus 1. I did the opposite than I normally do. But we can make that the same. So this is now going to be 1 minus 1, 0, 0, 0, 0. And this tells us that x minus y is equal to 0. Or in other words, x is equal to y. And just like before, we have a free variable right here. So y is just going to be equal to y. And we get that the eigenvector xy is going to be 1, 1 times y. So this tells us right here that 1, 1 is an eigenvector of A with eigenvalue 10. And for emphasis, this is actually a line. It says any vector on the line spanned by the vector 1, 1 is in fact also an eigenvector. But it's fair to say, okay, you pick one of them. So the eigenvector is 1, 1. All right, so we found the eigenvector with all the eigenvalues. And so now we can encode A. So this is the finale. That what we can do is we can write our matrix by diagonalizing it. let's diagonalize A. So this is our matrix A, and we can write A as S, D, and S inverse. So we're going to have an S, a D, and an S inverse. So we have our first eigenvector. And when I say eigenvector, we just have to pick one of them. The key thing is that S needs to be linearly independent. So we need to make sure that we have one eigenvector for every eigenvalue. There's going to be a mild wrinkle to that in another example we're going to do in a second. But for every eigenvalue, we need an eigenvector. And we're going to add a little layer of a complexity onto that in our next example. So our first eigenvector, this was for that was our eigenvector with eigenvalue 8. And then here was our eigenvector with eigenvalue 10. And then we have S inverse over here. All right, so this is how you diagonalize A. And just for emphasis, right, for fun, what this says is we can take this matrix to a very large power. I can take, say, 100. And I know without computing anything that this is going to be equal to 1 minus 1, 1, 1 times 8 to the 100 times 10 to the 100 times the inverse of S. So the power of diagonalization is it tells us very easily what the higher power, any power of the matrix is, without actually computing it out 100 times. And intuitively, it also gives us the long-term behavior. This matrix is going to grow roughly by a factor of 10 at each iteration. By a factor of 10, and at worst by a factor of 8. So that's how these eigenvalues come into play. And this is kind of why we care about it. So we can look at higher powers. Okay, so this is kind of an overview of the full process of computing an eigenvector and eigenvalues, then computing the eigenvectors using the solution. So for every lambda, you're going to get a solution. And then you can put them together and form the diagonalization, which lets you compute higher powers of your matrix. Okay, so let's focus on a 3x3 example. And we're going to compute the eigenvalues and eigenvectors of this guy. Okay, so this is just the same thing as before. We're going to compute the determinant of A minus lambda I. So we're just going to take this guy right here. And we're going to subtract on the diagonal lambda. And then we can compute the determinant. So here there's going to be 3 positive entries. And this is going to be upper triangular. So we're just the only term that's actually going to play in a role is this first one. And the other 2 are going to be 0. And likewise for the negative side, you're going to have the 3 negative. Now each of these are going to be 0. There's at least 1 0 in one of those diagonals. So we're going to get minus 0, minus 0, and minus 0. So here we have an upper triangular matrix. In general, calculating the determinant of these may take a while and solving them, but here it falls right out. So for sake of brevity, I use an upper triangular matrix. So our characteristic polynomial is now 1 minus lambda times minus 2 minus lambda. And to find the eigenvalues, we're going to take this and set it equal to 0. We're solving this as the determinant of A minus lambda I, and we set it equal to 0. And now the solutions just fall right out because it's already factored. So we have one factor of lambda equals 1, another factor of lambda equals 1, and one factor of lambda equals minus 2. So this is an important example of what's called the algebraic multiplicity. And it's just the number of times it appears as a factor in the characteristic polynomial. What the algebraic multiplicity is going to indicate is a maximum of how large the dimension can be for the corresponding vector space for that eigenvalue, the corresponding eigenspace. So to see this, let's go ahead and just dive into finding the eigenvalues. And we're going to do this just by solving a minus lambda I x is equal to 0. So we're solving for vectors x. And just as for emphasis, we do this for each lambda. So we have to do it once for lambda equals 1. So we're going to go back to our matrix right here. And we're going to do subtract lambda equals 1 on the diagonal. So that we're going to subtract 1 on the diagonal here. And we're going to solve for when this is equal to 0. And so if we use an augmented matrix, we're going to get 0, 0, 2, 0, 0, minus 1, 0, 0, minus 3. And that's going to equal 0, 0, 0. So we're going to row reduce this guy. So we're going to just take row 1 and multiply it by a half. And then we're going to take the other ones and reduce them away. And we're going to get, this does not reduce to the identity. And indeed, we have this. This indicates right here, now we have two free variables right here. And this last free variable, this last row, this is an unusual case where the missed pivots are actually not the later columns, but the first columns. So this column here indicates that we have z has to be equal to 0. And the free variables tell us that we have x equals x and y equals y. So now we have a strange case where the solution set to this equation, to our original equation, was x, y, z. One of them is given by here. We can change x, and every time we change x, it only affects x. Or we can change y. And so this right here, this is the solution to ax minus 1, a minus 1 lambda, a minus 1 I. A minus 1 I. Lambda is 1. This is the solution of this equation. And for emphasis, any solution to this is an eigenvector with eigenvalue 1. And so the set of all the possible eigenvectors with eigenvalue 1 here are going to form a plane. They're going to form a vector space of dimension 2. So in much the same way that when you pick an eigenvector, we care about picking ones that are not linearly independent, or for example, in the 2 by 2 example, we don't want to pick a scalar multiple of one that we've already done. If you have duplicated eigenvalues, that means the dimension is going to be higher. This is called the geometric multiplicity. And as a warning, the algebraic multiplicity of an eigenvalue is not always its geometric multiplicity. So it's possible that you solve the characteristic equation and get multiple instances of the same root, and then you go to solve a minus lambda I x equals 0 and find the eigenvectors, and you can't find them. This is possible. But when we have a higher dimension for an eigenspace, or the vector space for those eigenvalues, the key thing is that when we diagonalize it, which we'll do in a second, or later after we find the other eigenvectors, that you pick some that are linearly independent. So we can pick any combination of 1, 0, 0, and 0, 1, 0. Though any combination of those vectors are going to form an eigenvector. But when we diagonalize it, we want to pick two of them that are linearly independent. We want to pick a basis for this eigenspace. Now, and here is these two vectors are the basis for that eigenspace. So we can just pick those two, but you can pick any two that you want as long as they're linearly independent. So we have two eigenvectors there with eigenvalue 1. And now we can go back, and we have to do this for each lambda. So we're going to go back and do it for lambda equals 2. So we're just going to solve this one for this one equals 0. Oh, so this would be a plus 2. That's what's wrong. So this is a common mistake here. This is minus 2. So that becomes a plus. So this should be a 3, and a 0. Okay, so then we make this an augmented matrix. And now we're going to row reduce this one. So we're going to take 1/3 row 1. And hopefully you can see that this last row, because it's all zeros, we're not going to get to the identity. So we're going to get a non-trivial solution, which is going to be our eigenvector. All right, and then we're going to, this one's already set, so we can do this one. So we're going to do 1/3 row 2 into row 2. And now we're done because this is in reduced echelon form. There's the staircase, only leading ones. We have one mispivot column in the third column. So that means that we're going to have z's just free. So we're going to choose what z is. But this top row says x plus z, 2/3 z is equal to 0, and y minus 1/3 z is equal to 0. So this tells us that x equals minus 2/3 z, y is equal to 1/3 z, and if z is equal to z. So if we pick z, we automatically get that the vector xyz has to be minus 2/3, 1/3, 1 times whatever we pick for z. And this is going to be our eigenvector with eigenvalue 2. All right, so we can go back to the grand finale now. And we can diagonalize this matrix. All right, so we can take our matrix and we can write it as, we're going to have an S, a D, and an S inverse. All right, and we're going to be able to do this because we had two eigenvalues of eigenvalue 1. So these were the eigenvalues 1 had multiplicity 2. So we're going to go back and we're going to find a basis for that solution space. That's the basis. You can pick whatever basis you want. So just like in the 2x2 case, you can pick any scalar multiple of the eigenvector you want. It doesn't matter. And here, when you have an eigenspace with a higher dimension, you can pick whatever vectors you want as long as you pick a basis for your solution. So here, the basis vectors are just the ones right in front of you, but you could pick a different ones. But we'll pick those for now. And then we have this other vector right here, the minus 2/3, 1/3, 1. And this corresponds to the eigenvector with eigenvalue 2. So now we have a diagonalized matrix. And so that's how you can diagonalize a larger matrix that has repeated eigenvalues. So as a note, right, if the algebraic multiplicity is not equal to the geometric multiplicity, then you're not going to be diagonalizable. And this is for any lambda. So for any lambda, if for one of the lambdas it was the case that it just didn't work out, that you didn't get two solutions here. So going back to here, when we solved the characteristic equation, we got two factors of 1. If we solved ax minus a minus lambda I and didn't get a two-dimensional solution space, then we wouldn't be able to do this grand finale and we'd be short right here. And so if you can't do that, then you're not going to be diagonalizable. So having the algebraic multiplicity and the geometric multiplicity is having them coincide, having them be equal is important for diagonalizability. We're not going to go into how you can correct that using some other methods, but this is kind of a rare instance and is only going to come up when you have the same eigenvalue repeated and the eigenvectors kind of mess up in a certain way.